December 1944. The Ardennes forest. -15 degrees Celsius. Schwer SS Panzer Abteilung 50. One musters 45 King Tigers on paper, though mechanical problems have already reduced operational strength to barely 30. These surviving behemoths grind forward through frozen Belgian roads, their exhaust plumes rising like smoke signals against the grey winter sky. Kampfgruppe Piper, the spearhead of Hitler's last desperate gamble in the West, commands a force that should terrify any opponent. At its core sit the fearsome Tiger IIs, the King Tigers, and each one a 70-ton monster wrapped in 150 millimeters of sloped armor. Their 88 millimeter guns can punch through any Allied tank at distances exceeding 2,000 meters. Their crews are veterans of the Eastern Front, hardened killers who have faced Soviet armor and won. On paper, nothing in the Allied arsenal can stop them. But the King Tiger carries a secret that no amount of armor can protect against, a fatal flaw that will doom this offensive before it truly begins. These mechanical leviathans drink fuel at rates that defy comprehension, 500 liters per 100 kilometers on good roads, rising to 800 or more cross-country. Their massive Maybach engines, originally designed for tanks weighing half as much, strain and overheat under loads they were never engineered to handle. Transmissions designed for 50-ton vehicles crack under the 70-ton weight of a fully loaded King Tiger. Final drives shatter with alarming regularity. And the fuel, the precious fuel that keeps these steel beasts alive, runs out faster than any supply column in German service can deliver. By December 23rd, just 7 days into the offensive, Kampfgruppe Piper receives permission to withdraw. The spearhead has been virtually without fuel for over 2 days. The most powerful armoured formation Germany has ever assembled for a single operation grinds to a halt, not because American guns have destroyed it, but because it simply cannot feed itself enough gasoline to keep moving. What happens next reveals everything you need to understand about why Germany lost the tank war, despite building what many historians consider the finest armoured vehicles of World War II. The German commanders face an impossible choice. They have tanks, they have crews, they have ammunition. They do not have fuel. Rescue is impossible. The roads behind them are choked with traffic, ambushed by American forces, interdicted by Allied aircraft whenever the weather clears. No tanker trucks are coming. No airdrop can deliver enough fuel to matter. So they abandon 6 fully operational King Tigers, 13 Panthers, 7 Panzer IVs, not damaged by enemy fire, not destroyed in combat, simply stuck, out of fuel, out of options, out of time. The crews place demolition charges inside the tanks they have lived in and fought in, and kept running through countless battles. They blow up their own vehicles to prevent capture, destroying more combat power than most Allied divisions possess. Then they shoulder their personal weapons and escape on foot through the frozen forest, leaving behind the smoking hulks of Germany's finest armoured technology. This is the story that popular history often forgets. The story of how Germany built the biggest tanks, the most powerful tanks, the most technologically sophisticated tanks of the Second World War, and how America built something far more valuable, the tank that kept running. To understand how Germany made perhaps the greatest strategic miscalculation of the armoured age, you have to travel back to 1941, and a battlefield that changed everything. German commanders thought they knew about tank warfare. When Wehrmacht forces first encountered the Soviet T-34 in the summer of that year, they experienced something close to technological shock. German panzer crews watched in disbelief as their shells bounced off sloped armor they had never seen before. The T-34 mounted a 76 millimeter gun more powerful than anything German medium tanks carried. Its diesel engine propelled it faster than German commanders believed possible for a vehicle of its size. Its wide tracks let it cross terrain that bogged down German vehicles. Panzer generals sent frantic reports back to Berlin. Their Panzer IIIs and IVs, the reliable workhorses that had conquered Poland and France and driven deep into the Soviet Union, suddenly seemed obsolete. Something had to be done, something dramatic. Hitler's response would shape German tank doctrine for the remainder of the war, and it represented a fundamental philosophical choice about what a tank should be and what role it should play. The Germans chose perfection over production. They chose quality over quantity. They chose individual superiority over mass logistics. History would prove each of these choices catastrophically wrong. The Tiger program that emerged from this crisis produced a tank unlike anything the world had seen. The Tiger I weighed 57 tons, nearly twice the mass of German medium tanks. It mounted the legendary 88mm gun, originally an anti-aircraft weapon that German crews had discovered could destroy any tank in existence. Its armor, 100mm thick on the front, could shrug off hits from virtually any Allied gun at combat ranges. But creating this mechanical marvel required resources Germany increasingly could not spare. Each Tiger I demanded an estimated 300,000 man-hours to produce. 300,000 hours of skilled labor from machinists, welders, electricians, assemblers, testers, and quality control inspectors. Compare that to approximately 48,000 man-hours for a Sherman by some estimates. For every single Tiger that rolled off the Henschel production line, American factories could produce roughly 6 Shermans. The production disparity was even worse than those numbers suggest, because American industry was expanding while German industry was contracting. American factories ran 3 shifts. American workers received adequate food and housing. American supply chains delivered materials reliably. German factories faced labor shortages, as workers were drafted to the front. German workers endured rationing and bombing. German supply chains collapsed under the weight of Allied interdiction. Yet production numbers tell only part of the story. The Tiger's problems ran far deeper than how long it took to build. German engineers designed the Tiger as if they had unlimited resources, unlimited time, and unlimited supply lines stretching from factory to front. Every design choice optimized performance without considering the practical realities of maintaining these vehicles in combat conditions. Consider the Tiger's innovative interleaved road wheel system. German designers used overlapping wheels because this arrangement provided excellent weight distribution, reducing ground pressure and allowing the Tiger to cross soft terrain that would have swallowed lighter tanks. The engineering was elegant. The maintenance implications were disastrous. When a road wheel failed, as road wheels inevitably do after thousands of kilometers of use, mechanics could not simply unbolt it and attach a replacement. The interleaved design meant that to reach an inner wheel, crews had to remove up to 9 outer wheels first. A repair that took Sherman mechanics 30 minutes could consume an entire day of Tiger maintenance time. On the Eastern Front in winter, mud and snow would freeze solid between the overlapping wheels overnight, sometimes immobilizing tanks until crews could chip away the ice with hand tools. The 88mm gun was devastating in combat, capable of destroying any Allied tank at ranges where those tanks could not effectively respond. But manufacturing this weapon required precision machining tolerances that German industry struggled to maintain as the war dragged on. Allied bombing disrupted the supply of specialized steel alloys. Skilled workers died on the Eastern Front faster than they could be replaced. Quality control suffered under production quotas that demanded ever more tanks from ever fewer resources. The armor itself created problems that German designers never fully solved. Thick, overlapping plates required perfect welds to maintain structural integrity. As welding quality declined, tanks left factories with hidden weak points that became death traps when hit by enemy fire. The sheer mass of all that armor strained every mechanical system. Which brings us to the fundamental problem: weight. The Tiger I weighed 57 tons. European infrastructure was not designed for vehicles of this mass. Most bridges across the continent had load limits of roughly 40 tons, suitable for civilian trucks and the medium tanks that armies had used since the First World War. The Tiger exceeded these limits by 17 tons. Every advance required German combat engineers to survey bridges along the route, calculate load capacities, and determine whether reinforcement was possible. When it was not, they had to find alternate crossing sites, often fording rivers that exposed tanks to enemy observation and fire. Every retreat left Tigers stranded when bridges they needed had already been destroyed by rearguard forces. Recovery of immobilized Tigers required specialized equipment that was rarely available when needed. Railroad transport presented even greater challenges. The Tiger was too wide for standard European rail clearances. Those interleaved road wheels that worked so well in the field created a track width that simply would not fit through tunnels and past platform edges designed for narrower vehicles. Before loading a Tiger onto a train, crews had to remove the outer road wheels and replace the combat tracks with special narrow transport tracks. This process consumed approximately 2 hours. Upon arrival at the destination, crews repeated the process in reverse, reinstalling combat tracks and road wheels before the tank could move under its own power. When Tigers arrived at their detraining point, they often found themselves 30 or 40 kilometers from the actual combat zone, forced to drive to the front and burn precious fuel while accumulating wear on already stressed mechanical systems. Yet even as these problems became apparent in combat reports and maintenance logs, Hitler demanded more of what was already failing. Bigger, heavier, more powerful, always more. The King Tiger that followed weighed 70 tons and consumed fuel at rates that would have been comical if they were not tragic. The Maybach engine that powered it produced 700 horsepower, giving the vehicle a power-to-weight ratio of approximately 10 horsepower per ton. For comparison, the Sherman achieved roughly 14 horsepower per ton. The King Tiger accelerated like a loaded freight train and climbed hills at a crawl, its engine straining under the massive burden. The Panther tank represented a different approach that still fell into the same trap. Originally specified at 30 to 35 tons as a lighter, more producible response to the T-34, the Panther grew heavier through armor additions and design changes until production models weighed 45 tons. By the end of the war, fully loaded Panthers weighed even more. And then there was the Maus. The name means mouse in German, an ironic joke for the largest tank ever built. 188 tons of steel, armor, and hubris concentrated into a single vehicle that represented everything wrong with German military engineering philosophy. The Maus mounted 2 guns, a 128mm main armament, and a coaxial 75mm secondary weapon. Its armor exceeded 200mm in places. On paper, it was invincible, unstoppable, the ultimate expression of armored warfare. In reality, it had a design top speed of 20 km per hour, though the prototype only managed 13. It could not cross any bridge in Europe. Its engines drank fuel faster than any logistics system could deliver. Its weight caused it to sink into any ground softer than concrete. The suspension system required constant maintenance just to function. Only 2 prototypes were ever completed, and neither saw combat. Soviet forces captured them in the factory where they were built. The Maus remains the perfect symbol of German tank philosophy, taken to its logical, absurd conclusion. A weapon so powerful it could not fight, so heavy it could not move, so complex it could not be produced, so thirsty it could not be fed. A monument to engineering excellence deployed in service of strategic blindness. Meanwhile, 3,000 miles away, across an ocean that German submarines could not close, American engineers made entirely different choices based on entirely different assumptions. The M4 Sherman was not designed to be the best tank in the world. It was designed to be the best enough tank that America could build by the tens of thousands, ship across the Atlantic and Pacific, maintain with mechanics who had trained for weeks instead of years, and keep running day after day in deserts and jungles and frozen forests until the enemy surrendered or was destroyed. The difference in philosophy would prove decisive. When American planners sat down to design their primary medium tank, they started with a question that German designers apparently never asked. How do we build 40,000 of these things? The question led to other questions. How do we ship them across an ocean on cargo vessels that have to carry everything else an army needs? How do we get them off beaches under fire? How do we move them by rail across a continent? How do we keep them running when trained mechanics are scarce and spare parts come from factories 5,000 miles away? The answers shaped every aspect of Sherman design. Averaging around 33 tons combat loaded depending on variant, the Sherman could cross every bridge in Western Europe without reinforcement or bypass. It could roll onto standard railroad flat cars without modification, track width size to fit through tunnels and past platforms. It could load and unload from cargo ships using standard dockside equipment. It could be carried in the holds of Liberty ships that American yards produced at a rate of 3 vessels per day. The vertical armor that critics disparaged offered one significant advantage. It was easy to manufacture. Sloped armor required complex forming processes and precise welding angles. Vertical plates could be cut and assembled by workers with minimal training, using equipment available in factories across the American industrial base. But the truly revolutionary aspect of Sherman design was its flexibility in propulsion. American engineers created a tank that could accept multiple different engine types, each with its own characteristics and supply chain. The Continental R975 radial engine came from aircraft production, a proven power plant with a well-established manufacturing base. The Ford GAA-V8 was designed specifically for tanks, offering good performance with relatively simple maintenance requirements. General Motors contributed the 6046 twin diesel, which shared components with engines the company was already producing for other military vehicles. Chrysler developed perhaps the strangest solution of all. The A57 multibank engine combined 5 automobile engines into a single power plant through an elaborate gear arrangement. It was mechanical complexity of a peculiar sort, using simple components in a complicated arrangement rather than complicated components in a simple arrangement. Any mechanic familiar with Chrysler automobile engines could work on individual cylinders. The arrangement let Chrysler contribute to tank production without retooling for an entirely new engine design. This was not elegant engineering by German standards. Some of these solutions were frankly bizarre, but the approach meant something crucial for the reality of total industrial war. When Continental could not deliver enough radial engines because aluminum supplies ran short, Chrysler could step in with its automotive adaptation. When diesel fuel proved more available than gasoline in certain theaters, diesel engine Shermans could be deployed preferentially. When any single supplier faced problems, production never stopped because alternatives existed. The results spoke in numbers that drowned out any theoretical arguments about armor angles and gun penetration. Between 1942 and 1945, American industry produced 49,324 Shermans. Pause to consider what that number means. It exceeds the total German production of all tank types combined across the entire war. Germany produced roughly 1,200 Tigers, approximately 6,000 Panthers, and around 8,500 Panzer IVs, plus various assault guns and tank destroyers. American Sherman production alone exceeded all of those categories added together. In December 1942 alone, the Detroit tank arsenal turned out nearly 900 Shermans. That single month of production from a single factory nearly equaled total Tiger production across the entire war. German tankers might destroy 3 Shermans in a single engagement and celebrate their victory. By the next morning, American logistics would have replaced all 3 with fresh vehicles drawn from massive depots behind the lines, and the attack would resume with undiminished strength. This was not a failure of Allied tank design. This was the design working exactly as intended. Yet production numbers alone do not explain the Sherman's true advantage over its German counterparts. That advantage lay in something far less glamorous than penetration statistics or armor thickness, but infinitely more important in the context of sustained industrial warfare. Reliability. When a Sherman engine failed in the field, which happened far less frequently than with German vehicles, crews could replace it within a few hours using field maintenance equipment. Trained mechanics performed the operation routinely. The new engine started, the tank drove away, and combat operations continued. When a Tiger engine failed, the vehicle often had to be evacuated to a rear area depot for repairs. Recovery itself was problematic because the Tiger's weight exceeded the capacity of most recovery vehicles. Frequently, 2 or 3 recovery vehicles had to work together to tow a single disabled Tiger. The repairs themselves could take days or weeks, and parts were frequently unavailable. Sherman transmissions rarely failed under normal use. Tiger transmissions failed so frequently that German maintenance manuals recommended complete rebuilds after just a few hundred kilometers of operation. According to a French post-war evaluation, the Panther's final drives, a critical component connecting the transmission to the tracks, had an average fatigue life of only 150 kilometers before requiring replacement. British military intelligence conducted extensive studies comparing tank reliability across all combatant nations. Their conclusion was unambiguous and damning for German design philosophy. American tank construction was so infinitely superior in every other way, particularly in reliability, that theoretical shortcomings in armor protection and main armament became secondary considerations in practice. A British officer testing a captured Sherman during a 1943 long-distance service trial recorded his observations in language unusual for military documentation. He described the vehicle as utterly reliable in conditions that would have reduced any German tank to a maintenance casualty. The Americans, he noted, had built a tank that actually worked. The numbers from combat operations tell this story with statistical clarity that no amount of propaganda could obscure. In August 1944, according to Steven Zaliger's comprehensive analysis of readiness data across all fronts. American armored divisions reported operational readiness rates of approximately 85%. 85 out of every 100 tanks were running, fueled, armed, and ready to fight. German heavy tanks in the same period struggled to maintain comparable readiness. Panthers achieved approximately 51% operational status. Tigers fared even worse at around 48%. Nearly half the tanks in a German heavy tank unit might be sitting in maintenance parks at any given time, waiting for parts that were not available or repairs that required skills not present. The implications were strategic rather than merely tactical. The most powerful tank in the world is worthless when it is sitting in a repair depot awaiting spare parts that will never arrive. A Tiger that cannot move cannot fight. A Panther waiting for transmission replacement cannot hold a defensive position. Combat power exists only when vehicles are operational. Field reports from both the Eastern and Western fronts document this disparity with brutal clarity. The American 3rd Armored Division noted that its Sherman battalions completed long road marches of hundreds of kilometers with negligible mechanical losses. Tanks that started the march finished the march. Units arrived at their objectives with their combat power intact. German panzer units making similar movements routinely lost 20% or more of their strength to mechanical breakdowns before reaching combat. Units would set out with 40 operational tanks and arrive with 32, the remainder scattered along the route of march awaiting recovery vehicles that might never come. One German maintenance report captured after the war's end revealed the nightmare facing panzer crews trying to keep heavy tanks operational. For every hour a Tiger spent in combat, it required 10 hours of maintenance. Engines rated for 1,500 kilometers between overhauls frequently failed after only 300. Transmissions designed for the theoretical 50-ton weight of the original Tiger specification could not handle the actual 57-ton weight of production vehicles. The Panther's combat debut illustrated these problems with catastrophic clarity that shocked even German commanders who had thought themselves prepared for teething troubles. In preparation for Operation Citadel, Germany's last major offensive on the Eastern Front, planners committed 200 of the revolutionary new Panther tanks to the attack against the Kursk salient. This was to be the Panther's proving ground, the battle where Germany's answer to the T-34 would demonstrate its superiority and restore German armored dominance in the East. What happened instead became a cautionary tale about rushing unproven technology into combat. 2 Panthers caught fire while being unloaded from the trains that delivered them to the front. The exact cause was never definitively established, but fuel system problems were suspected. More broke down during the approach march from the railhead to the assembly area, their engines overheating or transmissions failing before they ever saw combat. By the morning of July 5, 1943, when the offensive began, only 184 of the original 200 Panthers were operational. Within 2 days of combat operations commencing, that number collapsed to approximately 40 runners. By July 10th, German reports indicated as few as 10 Panthers remained combat-ready. General Heinz Guderian, the legendary architect of German blitzkrieg doctrine, the man whose tactics had conquered France in 6 weeks, found serious deficiencies in the final drive and engine, and considered it a grave mistake to deploy the Panther before it was ready. Analysis of Panther losses during the Kursk offensive revealed a devastating truth about mechanical reliability. Of the Panthers lost during the battle, the majority succumbed to mechanical failure rather than enemy action. Engines died, transmissions shattered, fuel systems leaked, electrical systems failed. The tanks that were supposed to win the decisive battle of the Eastern Front could not survive their own machinery long enough to reach the enemy in significant numbers. Reliability concerns extended far beyond the front lines to encompass the entire logistics chain that sustained modern armored warfare. An American armored division consumed approximately 45,000 gallons of fuel per day during active operations. This was a significant logistical burden, but one that American supply infrastructure could sustain through its extraordinary transportation network of trucks, pipelines, rail, and improvised solutions. The Red Ball Express, the truck convoy operation that supplied Allied forces after the Normandy breakout, moved over 400,000 tons of supplies in its 3 months of operation. A German panzer division equipped with heavy tanks required proportionally more fuel per vehicle while fielding fewer vehicles overall, and German supply infrastructure was never designed or equipped to support such demands across extended operations. The Tiger I consumed approximately 430 litres of fuel for every 100 kilometres travelled on roads, rising to nearly 700 litres cross-country. Combat operations involving frequent acceleration and manoeuvring could push consumption even higher. The King Tiger was even thirstier, 500 litres per 100 kilometres on road, rising to 800 or more cross-country. In difficult terrain with hills to climb and mud to cross, consumption could exceed any reasonable estimate. When planners designed the Ardennes offensive, they allocated fuel for Kampfgruppe Peiper to travel approximately 90 to 100 miles, enough to reach the first major objectives if everything went perfectly. The ultimate objective, the Meuse River crossings that would open the road to Antwerp and potentially split the Allied armies, lay nearly twice that distance away. German planning assumptions relied on capturing Allied fuel dumps along the route of advance. This was not contingency planning. It was operational necessity. Without captured fuel, the offensive would stall before reaching its objectives regardless of tactical success. At the Belgian town of Bullingen, Peiper's leading elements did capture an American fuel depot containing approximately 50,000 gallons of gasoline. It should have been a triumph that solved the spearhead's supply problems. But the panicked American retreat and German mechanical breakdowns had scattered Peiper's column across miles of narrow, frozen roads. Vehicles were not where they were supposed to be. Radio communications were unreliable. Tanker trucks carrying the captured fuel drove forward to supply the lead elements, while tanks in the middle of the column sat immobile with dry tanks, waiting for resupply that went past them to units ahead. By December 19th, 3 days into the offensive, fuel consumption had exceeded all planning estimates. Tanks idled for hours in traffic jams on roads too narrow for vehicles to pass each other, engines running and fuel burning, while crews waited for routes ahead to clear. Others climbed steep Ardennes hills at full throttle, drinking gasoline faster than any supply system could deliver. The supreme strategic irony of the Ardennes offensive is that Germany's most powerful armoured spearhead was defeated not by American tanks, or American infantry, or American artillery, but by American logistics. While Kampfgruppe Peiper ran dry, American supply officers were routing fuel trucks around threatened areas, maintaining the steady flow that kept Allied Shermans running and Allied counterattacks building. Popular mythology remembers certain dramatic engagements that seem to prove German tank superiority beyond question. None has achieved greater fame than the action at Villers-Bocage. On June 13, 1944, exactly 1 week after the Normandy invasion, SS Hauptsturmführer Michael Wittmann spotted a British armoured column halted on a road near the Norman town of Villers-Bocage. The British had advanced into a gap in German defences and paused to reorganise. Their tanks lined up on the road in march column rather than deployed for combat. Wittmann seized the opportunity with the boldness that had made him one of Germany's most celebrated tank commanders. Leading elements of his company, he attacked immediately. In approximately 15 minutes of furious action, Wittmann and his fellow Tiger commanders from 2nd Company, 101st SS Heavy Panzer Battalion destroyed between 13 and 14 British tanks, plus numerous transport vehicles. The column was shattered. The British advance through the gap was stopped. This action has been celebrated for 8 decades as proof of the Tiger's absolute dominance and the superiority of German tank design and crew training. What the celebration ignores is equally instructive. Wittmann's company had driven nearly 300 kilometres from their assembly area near Beauvais to reach the Normandy front. It was a long road march, but not exceptional by the standards of armoured operations. American armoured divisions routinely covered similar distances during the campaigns that followed. Of the 14 Tigers that began that journey, only 5 or 6 arrived in operational condition. The rest broke down along the route, victims of the mechanical fragility that plagued every German heavy tank operation. Before a single shot was fired in combat, the company had lost more than half its strength to maintenance casualties. Wittmann's tactical triumph was real and deserves acknowledgement. It was also short-lived. Later that same day, British forces counterattacked with infantry, artillery, and armour. Street fighting erupted in Villers-Bocage. By the time the engagement concluded, up to 6 Tigers had been destroyed or abandoned in and around the town. German forces held the position briefly, but could not exploit Wittmann's tactical success into operational advantage. The British withdrew in good order. The German line stabilized but did not advance. And Michael Wittmann himself, Germany's most famous tank ace, was killed less than 2 months later, on August 8, 1944, near the village of Gaumsnil during Operation Totalize. His remains were not discovered until 1983. The exact circumstances of his death remain debated among historians. Some credit Trooper Joe Ekins of the 1st Northamptonshire Yeomanry firing a Sherman Firefly from long range. Others point to a Canadian unit, the Sherbrooke Fusilier Regiment, firing from concealed positions at close range, where even a standard 75mm Sherman could penetrate Tiger armor from the rear. What remains certain is that the tank propaganda portrayed as invincible met its end at the hands of Allied armor. This pattern repeated across the war with variations but consistent results. German heavy tanks achieved remarkable tactical successes in individual engagements. Skilled crews destroyed multiple enemy vehicles for every loss. Kill ratios favored German armor in nearly every direct confrontation. But those individual victories could never change the strategic reality that Germany was being ground down by enemies who could replace losses faster than German forces could inflict them. A Tiger that destroyed 5 Shermans before being disabled had achieved a tactical triumph. If 3 replacement Shermans arrived the next morning, the strategic calculation remained unchanged. German tank strength declined while Allied tank strength grew. The full scope of German heavy tank losses during the war was documented with characteristic thoroughness by German military record keepers. Unit war diaries and maintenance logs survived the war in sufficient quantity to provide historians with an unusually complete picture of how these vehicles met their ends. Analysis by historian Ron Klages of 1,718 recorded Tiger I and Tiger II losses reveals a truth that contradicts popular assumptions about these vehicles. Only 692 Tigers, approximately 40% of documented losses, were destroyed by enemy action in combat. Enemy guns and mines and aircraft accounted for less than half of German heavy tank losses. The remaining 60% were lost to causes that had nothing to do with Allied firepower. 341 Tigers were abandoned or became bogged in terrain from which they could not be recovered. Some sank in mud. Others became trapped in shell craters or building rubble. Many were simply left behind when retreating German forces could not arrange recovery. 260 were lost to mechanical failure, their engines dying, their transmissions shattering, and their electrical systems failing at moments when repair was impossible and abandonment was the only option. 57 ran out of fuel in locations where resupply could not reach them. Their crews, faced with the choice of capture or destruction, demolished their own tanks and attempted to escape on foot. 97 were blown up deliberately by German forces to prevent them from falling into enemy hands. These were often operational vehicles that could not be recovered during retreats, or tanks with minor damage that German industry could no longer repair. The King Tiger's loss record was proportionally even worse than its predecessor. Only 43% of documented King Tiger losses resulted from enemy combat action, compared to 54% for the original Tiger I. The bigger, heavier, supposedly more powerful successor proved even more likely to break down, run dry, or get stuck than the original. These statistics demolish any notion that German heavy tanks were worth their enormous cost in resources and production capacity. The majority of Tigers lost during the war were not destroyed by enemy fire. They were killed by their own complexity, their own insatiable thirst for fuel, their own crushing weight that broke bridges and roads and transmissions beneath them. Even German tank crews recognized the reality behind the propaganda. A report from Schwer Panzerabteilung 506, compiled by the staff of 16th Panzergrenadier Division in October 1943, stated bluntly that propaganda has made the Tiger out to be an invulnerable battering ram, but it can be knocked out by the T-34 at 500 meters. The men who actually manned these supposedly supreme weapons understood their vulnerability better than the generals who committed them to battle or the propagandists who celebrated their victories. The myth of German tank superiority survived the war itself, and in some ways grew stronger through decades of post-war mythology building. American veterans returned home with stories of Shermans exploding, of German tanks impervious to Allied guns, of 5 Shermans needed to destroy a single Tiger. Hollywood films depicted American tankers as hopelessly outgunned victims of superior German technology. This narrative became accepted as historical fact, but careful examination of wartime records tells a different story. Military historian Nicholas Moran conducted research that explained how the 5-to-1 myth originated. It stemmed from a fundamental misunderstanding of American tactical doctrine rather than any calculation of actual combat requirements. American tank platoons in World War II consisted of 5 tanks. This was organizational doctrine that applied to all tactical situations. When a platoon encountered a target, whether a German machine gun position, a concealed anti-tank gun, a Panzer IV, or a Tiger, the entire platoon engaged. 5 tanks maneuvered and fired together, because 5 tanks comprised a platoon, not because 5 tanks were required to defeat any particular target. Observers who witnessed 5 Shermans engaging a single Tiger assumed that all 5 were necessary to destroy it. They confused tactical organization with tactical requirement. The 5-to-1 ratio that entered popular consciousness reflected the size of an American platoon, not any calculation of how many Shermans a Tiger could actually defeat. Furthermore, American forces in Western Europe encountered the Tiger I extremely rarely across the entire campaign from D-Day to VE Day. Various estimates suggest American units engaged Tigers in combat perhaps 3 times during the entire 11-month campaign. The tank that supposedly terrorized American armored divisions was vanishingly rare on the Western Front. Panthers were somewhat more common but still represented a fraction of German armor strength. Most German tanks faced by American forces were Panzer IVs and various assault guns, vehicles that the Sherman could engage on roughly equal terms. The Sherman had real weaknesses that honest analysis must acknowledge. Its 75mm main gun struggled against the frontal armor of Panthers and Tigers at normal combat ranges. The later 76mm gun improved the situation, but was still not ideal for engaging heavy armor frontally. General Dwight Eisenhower himself expressed frustration when briefed on armor performance, reportedly asking in surprise whether the new 76mm gun could not penetrate Panther armor. He thought it was going to be the wonder gun of the war. The Sherman's vertical armor offered less theoretical protection than the sloped plates employed on German and Soviet designs. The interior layout concentrated ammunition in locations vulnerable to penetrating hits. Early models earned a grim reputation for burning when hit. But these weaknesses existed within a strategic context that fundamentally favored the Sherman's design philosophy. A Sherman that could drive 500 kilometers without mechanical breakdown could choose where and when to fight. It could maneuver around prepared defensive positions. It could flank heavier opponents. It could concentrate at decisive points while enemy heavy tanks sat immobile in repair depots. The men who lived and fought inside these machines understood combat realities better than any theorist far from the front. German tank crews wrote letters and reports documenting the constant struggle to keep their sophisticated vehicles running. One Tiger commander described spending more time waiting for repairs than actually fighting. Another noted the peculiar terror of advancing into combat, knowing that his tank might break down at any moment, leaving him stranded in front of enemy guns with no mobility and no hope of escape. American tankers complained about their Shermans too. They disliked the thin armor that German guns could penetrate at ranges where American guns could not respond effectively. They wanted bigger guns and thicker protection. Some nicknamed early Sherman models Ronsons after the cigarette lighter company whose advertising slogan was "Light's First Time," a grim reference to the tendency to catch fire when hit. But those same American crews could count on their tanks starting every morning. They could drive all day across rough terrain without watching temperature gauges climb into the danger zone. They could take a hit that disabled their tank and know that recovery vehicles would arrive within hours, that mechanics would repair the damage overnight or replace the entire vehicle within days, and that they would return to their unit combat ready. A Tiger stranded with a shattered transmission could do none of these things, regardless of how thick its armor was or how powerful its gun. American tankers learned to fight with the tools they actually had, rather than the tools they wished they had. They developed tactics that exploited their genuine advantages in numbers, reliability, mechanical endurance, and communications. When they encountered heavy German armor, they called in artillery concentrations and air support rather than charging frontally. They maneuvered to find flank shots rather than accepting frontal engagements on German terms. When they did engage directly, They usually prevailed through coordination and persistence, rather than individual vehicle superiority. When American engineers introduced wet ammunition stowage in later Sherman variants, surrounding the shells with water jackets that suppressed fires after penetrating hits, the tendency to burn catastrophically dropped to between 10 and 15% of penetrating hits, compared to 60 to 80% in earlier dry stowage models. German propaganda had created a reputation that American engineering methodically disproved. The real story of World War II tank warfare is not about which tank was best in hypothetical one-on-one combat or which vehicle had superior specifications on paper. It is about which tank philosophy best served the strategic needs of total industrial war. Germany chose quality. They built sophisticated weapons that demanded perfection from every component, every machinist, every supply line, and every crew member. When any element of that perfection was missing, the system failed. America chose quantity backed by adequate quality. They built straightforward weapons that could be produced by the tens of thousands, maintained by mechanics with months rather than years of training, kept running with parts shipped from factories an ocean away. Germany produced approximately 1,347 Tiger I's across the war. They produced roughly 489 King Tigers. America produced 49,324 Shermans. You can destroy 3 Shermans for every Tiger lost and still lose the war, when your enemy can build 6 Shermans in the time it takes you to build 1 Tiger. The mathematical calculation was inescapable. Germany's best tank crews achieved remarkable kill ratios that proved their individual excellence. But those ratios meant nothing measured against the flood of replacements that American industrial capacity could provide. The strategic blindness that created German heavy tank doctrine reflected a broader failure to understand the nature of the war Germany had initiated. Hitler and his generals designed weapons for short, decisive campaigns lasting weeks or months, the kind of operations that had worked in Poland and France. They never grasped that they were now fighting a grinding, industrial, years-long conflict where logistics and production mattered more than tactical excellence. They assumed German quality would always overwhelm enemy quantity. They never understood that American and Soviet industry could produce quality and quantity simultaneously, that adequate tanks in overwhelming numbers would defeat excellent tanks in insufficient numbers. By 1944, Germany was losing the war on every metric that actually determined outcomes. Production could not replace losses fast enough. Fuel supplies dwindled as Romanian oil fields fell to Soviet advances, and synthetic fuel plants came under sustained Allied bombing. Trained mechanics and skilled workers died faster than training programs could replace them. Rare metals needed for armor alloys became impossible to obtain as supply lines collapsed. The German response to this cascade of failures was to build heavier tanks that required more fuel, more maintenance, and more skilled labor to produce and operate. It was the strategic equivalent of a drowning man reaching for an anchor. The war ended not with a single climactic tank battle, but with the steady, grinding collapse of German logistics and industrial capacity. Tiger battalions that had achieved tactical victories in 1943 sat immobile in abandoned parking areas in 1945, their tanks dry of fuel or awaiting repairs that would never come. Factories that had produced Panther tanks were overrun by Soviet forces or bombed into rubble by Allied aircraft. Meanwhile, Sherman production continued at full capacity until August 1945, 3 months after Germany surrendered, and only because Japan's surrender ended the need for additional vehicles. American industry could have continued building thousands more Shermans if the war had required them. That reserve capacity, more than any technical specification or armor thickness or gun caliber, was the ultimate weapon of World War II. Germany built the biggest tank, 188 tons of engineering excellence that never fired a shot in combat. America built the tank that kept running. It drove from the beaches of Normandy to the heart of Germany. It pushed from North Africa through Italy to the Alps. It crawled from Pacific Island to Pacific Island until Japan surrendered. The lesson endures. In warfare, as in life, what matters is not what you can achieve at your theoretical best. It is what you can sustain every day, in every condition, when everything is going wrong. Germany designed tanks for perfect conditions that never existed. America designed tanks for the muddy, frozen, burning reality of industrial total war. The biggest tank lost. The tank that kept running won. If you found this exploration of World War II tank doctrine valuable, please consider liking this video and subscribing to the channel. Your support helps me continue producing thoroughly researched historical content that challenges the myths we have inherited. Click the notification bell to be alerted when the next video drops. Thank you for watching.